This interface can receive. And it also logs information locally. That is, it can receive messages. But it doesn't send messages. Under normal circumstances where our business is stable, it does not send any message. Secondly, this interface does not send business traffic. Any traffic that might loop these. It is not forwarded. So I can guarantee both. Under normal circumstances, this interface does not send data. It also ensures that if there is a problem with the other line, this interface can be automatically up. Then start forwarding. Like a button. If now in the network environment, there is a line forwarding, it can judge whether there is a loop in the network. If there is this port, block it. Blocking is not turning off. When it senses that other lines in the network have failed, then this interface is automatically up. Then start forwarding data traffic. This way it can be achieved without broadcast storm. No loop. It will not have MAC address drift. We can't talk more and more in depth in this class. The STP protocol is not commonly used now. It's not bad, because it actually has to block some interfaces. Everyone should know. This interface is very expensive. Modules actually have overhead. You will find, if this link is not forwarded now. In fact, the other party's interface is wasted. It is equivalent to running an STP now. You will now find, there will be a problem with your device. This interface appears to be, but in fact it does not forward. It's wasted. So in fact, STP is a waste of network resources. So now STP is not very practical. But we still have to learn it. Because the algorithm of this protocol is quite powerful. STP is actually design some ports to be logically blocked. Then the port that is blocked usually does not forward traffic. But it will store some packet of configuration information in STP. Once it finds that there are no loops in the network, then the port will be up. Start forwarding data. This is the characteristic of this protocol. Let's talk about how it is implemented in the next class. Let's introduce STP first. STP can simulate an acyclic tree in the network. It will have a sequence problem. A tree must first have a root. Then the root of the tree is called the root bridge in STP. Bridge means switch. The root bridge is the root switch. As a core node of the entire STP. In an environment, which device is the root device? Which device is the root bridge? We need to know how devices communicate. Let's take a look at the content of the courseware. For STP, you see there are 3 devices here. So among the 3 devices, let's go first. Since we are going to build a tree, where is the root of this tree? All 3 devices have the potential to be rooted. Then the choice of this root must have some parameter comparisons. Everyday devices can send some messages to each other. Comparison of size. It carries some parameters of the respective devices. Finally, a root device is elected through the election rules. Same. We also send messages. Select other things through some messages inside. This will be covered in the next lesson. We want to choose root bridge, root port, specified port. These 3 parameters. We have a message called a BPDU message. This is a message in STP. In this message, we'll carry all the parameters involved in the election. Are comparable. The devices send messages to each other through. Then elect various roles. In the NA stage of STP, it is actually the election of roles. For STP, the difficulty lies in the election rules. This BPDU message is called Bridge Protocol Data Unit. It is responsible for a message that determines the status of all information roles in the entire STP. The entire STP protocol is actually carry out overall communication according to BPDU message, just like an OSPF hello packet. In fact, there are two kinds of BPDU. A configuration BPDU. One is called TCN. This we will talk about in the next class. But all its messages are called BPDU messages. You need to know this. A message for all status role determination. All role states are determined by such messages. Before we formally talk about the content of this message, let's first look at a few core parameters in it. In the next class we're going to do some data comparisons. These four are the first ones we will mention in the next lesson. In this lesson, let's briefly talk about. First, have a root ID. Root ID is the bridge ID of the root. BID is bridge ID. It's a little hard to understand. There are many STP parameters, and not easy to understand. But you must know. BPDU messages will be sent between devices in the future. For example, many devices in one environment. This is a switch, not a router. They both send BPDUs. Assuming now it is a root. But in the root ID of all switches. At that time, the device thought that the root would be filled in. For example, now the root is device 1. Then in the packets sent by all devices, root IDs are all 1. Both device 2 and device 3 send 1. Prove it now thinks this device is rooted. It also considers itself to be. Then send to the downstream equipment. It will also carry 1 in it. Also consider it root. STP relies on such BPDU messages to maintain the overall relationship. Root will always send to other devices. Other devices will keep sending. It's like picking a boss in an environment. The boss must always tell others that he is the boss. It has been notifying other devices that it is now acknowledging it. This is called BID. This parameter is always the root bridge ID. Let's talk about how to represent this ID in the next class. Let's talk about RPC again. This RPC is short for root pass cost. Refers to the distance from the device to the root. Then for the root. Root self to self overhead is 0. How to calculate other devices to root. In fact, it will also be related to the interface. In the next lesson we will talk about. First understand. Let's talk about bridge ID and port ID at the end. This message will be sent down. For example, now this message is sent to switch B. Then if it is the root, it should be filled like this. First root ID is yourself. That is, me. RPC is 0. Bridge ID or yourself. That is, me. Say this is interface 1. Port ID this is 1. This is the message it sent out. Arrived at switch B here. Switch B also needs to receive packets. And send it down. Then the message sent by switch B. The root ID is still the switch A. This parameter will not change. RPC will describe the distance from switch B to switch A here. After that, the bridge ID will be changed to itself. This is called your own bridge ID. In the whole STP, all devices are called bridges. So it describes itself. This port ID is its own. That is, an interface on switch B. If you received a rooted device, that includes routing to downstream devices. It is then sent to the downstream device. Certainly. It's blocked here. Let's not talk about the blocking problem. Assuming it was sent out. It received. Then all this inside is the root. This is the root path overhead sent to that device. Let's take switch B as an example. Let's understand briefly. Let's talk about the rest in the next class. Okay. We'll stop here. Then we also hope that students can follow us. We are ThinkMo Education. I'm Grolin Annesley from ThinkMo. I hope today's content is helpful to you. See you next class. Bye classmates.